Welcome to Lesson 3 of Module 1, where we will cover some first examples of neural networks. Today, we will discuss different ways to apply the gradient descent method. Then, we will cover using various regularization methods to prevent overfitting. There are different ways the gradient descent method can be applied. We will cover a few. Recall that we measure the quality of estimates with a loss function by comparing the true values to predicted values. The goal is to find the weights that minimize this loss, and this can be done through the optimization algorithm of gradient descent. A loss function measures the estimation quality by comparing the true values to the predicted values from the model. The specific loss function shown is the mean squared error, which sums the square differences between the true and predicted values across all data points. The weights or coefficients of the model are represented by W, and N is the number of data points. Gradient descent is an optimization algorithm used to search for the weights that minimize the loss function. By iteratively adjusting the weights in the direction of steepest descent of the loss function, gradient descent can find a set of weights that provide a good fit between the model's predictions and the true data. This process is fundamental to training models like neural networks to perform well on tasks like regression or classification. The slide provides a concise review of these core concepts underlying the training process for machine learning models. Gradient descent works as follows. First, we choose a starting point, W0, for the model weights. Then, at each iteration, we update the weights by moving in the direction of the steepest descent of the loss function. This direction is given by the negative gradient or derivative of the loss with respect to the weights. The weight update rule shown subtracts the learning rate, eta, multiplied by the gradient from the previous weights. The learning rate determines the step size taken towards minimizing the loss at each iteration. The process continues for multiple steps t until convergence, with the weights tracing a path towards a local minimum of the loss function, as illustrated by the spiral trajectory in the diagram. You can manually set the learning rate, eta. If too small, it will update slowly, requiring more iterations to get to the optimal solution. If too large, it might overshoot the optimal solution. The objective function is usually the average of the loss functions for each example in the training dataset. For a dataset with n examples, the computing cost for each gradient descent iteration is O(n), which grows linearly with n. When the training dataset is large, the cost of gradient descent for each iteration is high. Stochastic gradient descent, which is sometimes abbreviated as SGD, reduces computational cost by randomly sampling only one training data instance to approximate the loss function at each iteration. In these formulas, the I represents the training data instance. This approach improves the computational cost, but it requires you to update the weights to consider only a single data point instead of the whole training dataset, and averaging. Therefore, it's more likely to cause a noisier weight update process, meaning more fluctuations in the loss value while training progress. Stochastic gradient descent is likely to cause a noisier weight update process because of the lack of data points that are considered in the process. Full batch gradient descent uses a whole data set and averages the outcome, which removes the noise. Noise here refers to the path that is not too smooth in the stochastic gradient descent compared to the full batch counterpart. In the figures on the slide, x1 and x2 refer to the axes for the two weights that are being updated. Think of each dot as W1 and W2. When moved from one dot to another, both W1 and W2 change. The full batch gradient descent approach computes gradients and updates model parameters using the entire dataset. This results in a smooth optimization path. However, this approach can be computationally expensive, especially for large datasets, as it requires processing the entire dataset for each parameter update. Additionally, if the data samples are similar or redundant, the full batch approach may not be efficient. On the other hand, stochastic gradient descent processes one observation at a time. This approach is computationally faster, as it avoids the overhead of processing the entire dataset for each update. However, the optimization path can be noisy and erratic, as the gradient estimates are based on a single data point and can be heavily influenced by noise in the data. Is another option available? Mini-batch stochastic gradient descent increases computational efficiency by randomly sampling a mini batch of training data instances to approximate the loss function at each iteration. A mini batch is obtained by a random permutation of the training data. In other words, each observation is processed only once, although in random order. The gradient update over a single observation is replaced by 1 over the mini batch, which stabilizes the optimization path. The number of batches is equal to the number of iterations in one epoch. For example, if you have 2,000 training examples, you can divide the dataset of examples into batches of 500. Then, it would take 4 iterations to complete one epoch. Note: most of the time mini-batch stochastic gradient descent is referred to as mini-batch gradient descent for short. The mini-batch size, denoted by B, is a crucial hyperparameter that can be manually set during the training process. Choosing an appropriate value for B is essential to achieve optimal performance and resource utilization. If the mini-batch size is too small, it results in a small workload, preventing the full utilization of compute resources, such as fast matrix multiplications in weight calculations. Conversely, if the mini-batch size is too large, it leads to a large workload, causing memory issues and wasting compute resources when the samples in the batch are identical. Therefore, the mini-batch size should be set large enough to offer good compute efficiency without causing memory issues. Now, let's discuss using regularization methods to prevent overfitting. Neural networks are prone to overfitting, especially when layers are added and neurons are added to layers. Regularization helps train machine learning models to generalize better beyond their training datasets. The 3 main regularization methods are early stopping, weight decay, and dropout. ML models go through different phases during training. If training stops too early, the model will remain unchanged from its random initialization, leading to underfitting. If training continues for an appropriate duration, the model will learn patterns that generalize well to unseen data, achieving a good fit. However, if training takes too long, the model will start to memorize the noise present in the training set, resulting in overfitting. When a model is trained for too long, its performance on unseen sets like validation or test sets might start to degrade, as indicated by metrics such as accuracy or average errors. Assume that you trained an ML model for 500 epochs. The figure shows training and validation loss as a function of epoch for a small example network. Note that the validation loss is minimized before 50 epochs, so training should be stopped at that time. Meanwhile, the training loss continues to decrease. Large weights make the network unstable. Although the weight will be specialized to the training dataset, minor variation or statistical noise on the expected inputs will result in large differences in the output. Generally, you can refer to this model as having a large variance and a small bias. In other words, the model is sensitive to the statistical noise in the training dataset. A model with large weights is more complex than a model with smaller weights. It's a sign of a network that might be overly specialized to training data. In practice, it's preferred to choose the simpler models with smaller weights, to solve a problem. With weight decay, you can keep the weights under control. The added term has a penalty coefficient and summation of squared weights. When weights change quickly and in large amounts, the model can overfit the data. An added penalty term makes it more difficult to overfit. The classical generalization theory suggests that simple models can help reduce overfitting. Therefore, aim for simple models. One way to achieve simple models is to simplify a given architecture by randomly removing some neurons from it. Due to its randomness, this process also forces the network to not easily memorize the training samples. This regularization technique is known as dropout. Dropout is one of the most popular regularization methods when training neural networks. This method randomly disables or removes neurons from a network. See the contrast between the 2 networks that are shown on the slide. When dropout is used, some neurons are randomly removed. To apply dropout, you need to set a retention probability for each layer. The retention probability specifies the probability that a unit is not dropped. For example, if you set the retention probability to 0.8, the units in that layer have an 80% chance of remaining active and a 20% chance of being dropped. Dropout is only used during training to make the network more robust to fluctuations in the training data. At test time, however, you want to use the full network. You shouldn't use dropout with the test data or during inference in production because, as you disable neurons randomly, your network will have different outputs for every activation or sequences of them. This undermines consistency. To summarize, early stopping is a technique that stops the training process when the model's performance on a validation set starts to degrade. This helps mitigate memorization, where the model overfits to the training data and fails to generalize well to new, unseen examples. Weight decay is another regularization method that penalizes large weight values in the neural network. By controlling how quickly the loss function changes, weight decay helps prevent overfitting by limiting the complexity of the learned model. Dropout is a regularization technique that randomly removes neurons or input features during training. This mitigates overfitting caused by false correlations in the data. In the next lesson, you will learn about different neural network architectures, such as convolutional neural networks and recurrent neural networks. Thank you.